Good day, everyone. For today's topic, we will be focusing more of one of the non-protein nitrogenous compounds that were discussed in your lecture, and that is uric acid. At the end of this laboratory briefing, the student must be able to review and recall what are the essential points about uric acid, its tests and methods in order for us to determine uric acid in the laboratory, the procedure on how it is done, and the reference range or the normal values for uric acid. So to help recall, what is uric acid? For biochemistry, you may say that uric acid is an organic compound with the chemical formula C5H4N4O3. We all know that it is the final oxidation product of purine metabolism in humans and higher primates. So the purines that I'm talking about here, if you can remember, what is it again? It's adenine and guanine. And purines are nitrogen-containing bases that are found in the DNA, RNA, ATP, and other nucleotides. And when these purines are broken down, uric acid is produced as the terminal catabolic product. Alright, so let's focus ourselves on the photo that I placed on the right side of the screen. The process usually begins when nucleic acids are degraded into nucleotides such as AMP and GMP. So what are these again? If you can remember, this is adenosine monophosphate and guanosine monophosphate. Very good. But aside from that, remember that nucleic acid degradation happens inside the body. Diet also plays a major role in the formation of uric acid. So this AMP class is converted into inosine and then hypoxanthine, while GMP is broken down into guanosine and then guanine. Guanine is converted into xanthine by the enzyme guanine deaminase, and both hypoxanthine and xanthine are oxidized by the enzyme. What is it again? If you can remember in your lecture, it is oxidized by the enzyme xanthine oxidase to produce uric acid. This enzyme is mainly active in the liver and small intestines and requires cofactors such as molybdenum, iron or sulfur, and fat groups to function effectively. Unlike most mammals class, they possess this certain enzyme which is used to convert uric acid into a more soluble compound. What do you call that enzyme? That is uricase. Correct. So this uricase class will convert uric acid into a more soluble compound. And what do you call this soluble compound? That is allantoin. Very good. We humans class lack the enzyme uricase due to an evolutionary gene mutation. As a result, uric levels in humans are naturally higher. Once formed, uric acid is then transported in the bloodstream primarily as a monosodium urate depending on the blood pH. So, at a normal physiological pH of about 7.4, it is largely ionized and soluble. But when levels become too high class, urate crystals can form, especially in the joints and in the kidneys. The excretion of uric acid is handled mainly by the kidneys, that's around 70%, and also in the excretion in the intestines, about around 30%. In the kidneys, uric acid undergoes filtration and then reabsorption, secretion, and then there is another post-secretory reabsorption, meaning only around 10% of the filtered uric acid is finally excreted in our urines. The intestines also play a role in excretion where certain bacteria can further break it down. Although uric acid is often associated with gout and kidney stones, It also serves important physiological functions. Number one, it acts as a strong antioxidant, neutralizing free radicals and protecting cells from oxidative stress. It can also scavenge reactive molecules such as hydroxyl radicals and peroxynitrite, helping maintain cellular redox balance. Furthermore, uric acid may have neuroprotective effects, such as studies that suggest that moderate levels help protect our central nervous system from oxidative damage, possibly reducing the risk of neurodegenerative diseases like Parkinson's and Alzheimer's. Evolutionarily class, the loss of uricase in humans may have been beneficial because the resulting higher uric acid levels could enhance antioxidant defenses and support longer lifespan and improved brain function. These are the clinical applications that are found in our reference books. Uric acid determination will help confirm diagnosis and monitor treatment of gout. It will also prevent uric acid nephropathy during chemotherapeutic treatment. It will also help assess inherited disorders of purine metabolism, will detect kidney dysfunction, and also assist in the diagnosis of renal calculi. Clinically class, the most common condition related to uric acid is hyperuricemia. Diba sometimes you can hear your parents say, sakit man akong joints, or you can also hear them say, probably this is my uric is nagsuol na sad, like that. Things like that. You would hear your parents say those words na probably uric na sad din ako. So this hyperuricemia class, this is a state where serum uric acid levels exceed the normal values. And it can be caused by a whole lot of reasons. Can be caused by overproduction of purines, can be decreased excretion by the kidneys, high consumption of purine-rich foods such as our favorite like red meat and seafood, and for those that are alcoholic, so if you have high alcohol intake, so this can also lead hyperuricemia, no? Remember that alcohol and seafood or red meat is a good combination. So this will really invite a lot of uric acid in our system. So beware, good class. Be careful lang. Or sometimes, another reason could be the use of certain medications like diuretics. And this hyperuricemia can lead to gout, which involves painful inflammation of joints due to urate crystal deposition, as well as kidney stones and a higher risk of metabolic and cardiovascular diseases. Conversely, low uric acid levels or hypouricemia may result from liver dysfunction, can also be due to excessive kidney excretion, or there is xanthine oxidase deficiency, or can be Wilson's disease. That's the reason why class uric acid testing is important, especially in diagnosing gout, monitoring renal function, and also assessing metabolic conditions. It is also used to monitor patients undergoing chemotherapy because there is rapid cellular breakdown when the patient is undergoing chemotherapy. And in doing so, there will be the release of large amounts of purines, causing dangerous uric acid accumulation in our patients. Regulation of uric acid levels can be achieved through both enzymatic and lifestyle means. As you already know, the enzyme xanthine oxidase controls the rate of uric acid production. And so as you can see there in our table, medications like allopurinol inhibit this enzyme to reduce uric acid formation. That's why it can cause decreased uric acid concentration. So if you know anyone class, you tell them that lifestyle adjustments such as avoiding purine-rich foods, also drinking plenty of water, they limit alcohol intake, and maintaining a healthy weight are also effective preventive measures. Let's now proceed to the summary of analytic methods in order for us to determine uric acid in the laboratory. We have already established, class, that most other mammals have the ability to catabolize purines to allantoin. And remember, this allantoin is very important because this is the more water-soluble end product. And this reaction is shown in this figure that I am showing you right now. You can see there that uric acid is readily oxidized to allantoin and therefore can function as a reducing agent in chemical reactions. This property, class, was exploited in early analytic procedures for the determination of uric acid. And the most common method of this type is the Caraway method, which is, by the way, is based on the oxidation of uric acid in a protein-free filtrate with subsequent reduction of phosphotungstic acid in alkaline solution to tungsten blue. However, class, even if this is the most common method, it is deemed non-specific and it's tedious because it requires protein removal. We also have different enzymatic methods in order to determine uric acid. Methods using uricase. Remember that uricase is the enzyme that catalyzes the oxidation of uric acid to allantoin. Remember that? So it can be uricase or urate oxidase. It's an enzyme with an EC number or enzyme commission number 1.7.3.3. This method is more specific and are used almost exclusively in clinical laboratories. The simplest of these methods measures the differential absorbance of uric acid and allantoin at 293 nanometers. And the difference in absorbance before and after incubation with uricase is proportional to the uric acid concentration. However, still, proteins can cause high background absorbance, which reduces sensitivity. Hemoglobin and xanthine can cause negative interferences as well. Another technique would be coupled enzyme methods or coupled enzymatic methods, which measures the hydrogen peroxide produced as uric acid is converted to allantoin. Peroxidase or catalase with an enzyme commission number of 1.11.1.6 is used to catalyze a chemical indicator reaction. The color produced is proportional to the quantity of uric acid in the specimen. Enzymatic methods, class, especially of this kind, have been adapted for use on traditional wet chemistry analyzers in the laboratory as well as for dry chemistry slide analyzers. However, if bilirubin and ascorbic acid, which destroys peroxide, if that is present in your sample in sufficient quantity, these substances could interfere with the reaction. That's why commercial reagent preparations often include potassium ferricyanide and ascorbate oxidase to minimize these interferences. While the use of a high-performance liquid chromatography can accurately determine uric acid levels in biological samples like blood and urine, offering a more reliable method with advantages such as good linearity and precision. The HPLC process involves using a reversed phase column and a mobile phase containing water, acetonitrile, and a buffer with the detection via UV or mass spectrometry at 260 to 285 nanometers. And lastly, isotope dilution mass spectrometry for uric acid determination involves adding a precisely known amount of a stable isotope labeled uric acid to a sample like serum, allowing it to equilibrate with endogenous uric acid. This mixture is then separated, often by chromatography, derivatized to make it suitable for mass spectrometry, and the isotope ratio of the labeled and unlabeled uric acid is measured to accurately calculate the original uric acid concentration. But as for our activity, we will be using Erba as our reagent, and we will follow this principle. See the principle there? You can see that uric acid is oxidized to allantoin by uricase with the production of hydrogen peroxide. And this hydrogen peroxide reacts with 4-amino antipyrine and DHBS. So you write it down, please. DHBS is 3,5-dichloro-2-hydroxybenzene sulfonate. So this DHBS class is a chemical used in colorimetric uric acid test. So when this hydrogen peroxide reacts with 4-AAP and DHBS with the presence of peroxidase, it will yield a red quinolamine dye. The absorbance of this dye at 505 nanometers is directly proportional to uric acid concentration in the sample. The reagents for this class is already in liquid form and it's ready to use. The reagent composition are as follows. By the way, there's no need to memorize the values. You only have to know what are the composition for R1 and what is found in R2. Also, for our specimen for this activity, we can use unhemolytic serum or heparinized plasma. We can also use EDTA plasma or 24-hour urine sample. Uric acid is stable in serum or plasma for 3 to 4 days at 20 to 25 degrees Celsius, that's room temperature. It is stable for 7 days at refrigerator temp, that's 4 to 8 degrees Celsius. Can be stable also for 6 months if you freeze the sample at negative 20 degrees Celsius. If you happen to run samples for 24-hour urine in the determination of uric acid class, in order to prevent the precipitation of uric acid, you have to add 15 ml of 5 moles per liter of sodium hydroxide into the urine collector to ensure that urine pH stays at greater than or more than 8. You have to dilute urine samples in 1:9 ratio with distilled water and multiply the results by 10. If ever the urine samples are contaminated, you have to discard them. As for the laboratory activity proper, you only need to pipette 2,000 microliter of the reagent and 50 microliter of the sample. Mix, incubate for 5 minutes at 37 degrees Celsius in the water bath. Measure the absorbance of the sample and the standard at 505 nanometers against reagent blank. By this time, you're already very proficient in calculating the results. So here's how you calculate again. The uric acid milligrams per deciliter, what you need to do is just substitute the change in absorbance of the sample over the change in absorbance of the standard. Multiply the concentration of the standard. I will be writing in the board during your laboratory activity about the standard or the calibrator's concentration so that you can compute. Class, the expected values that I placed here come from the reference ranges provided by our manufacturer, the reagent that we are using for this activity. Okay? So, please take note that adult males will have a reference range of 3.5 to 7.2 milligrams per deciliter. For adult females, it's 2.6 to 6.0 milligrams per deciliter. And for children, that's 2.0 to 5.5 milligrams per deciliter. In the laboratory class, we also do a 24-hour urine test for uric acid concentration. This test is a significant diagnostic tool used to evaluate how much uric acid the body produces and excretes over a full day. This test also provides more accurate and comprehensive information than a single random urine sample, since we know that uric acid levels can fluctuate throughout the day depending on diet, hydration, and metabolism. So, as you can see there, if the patient has an average diet, the expected values should be within 250 to 750 milligrams per deciliter. But if your patient has a high purine diet, it should be only less than 1,000 milligrams per deciliter. If the patient is given low purine diet, it should be around less than 480 milligrams per deciliter. But if your patient is given a purine-free diet, meaning no purine-rich foods in the food or diet of the patient, it should just be less than 420 milligrams per deciliter. In order for us to get the micromoles per liter, or to convert milligrams per deciliter into micromoles per liter, just simply multiply. Also, class, these reagents do not interfere with the following substances: hemoglobin up to 10 grams per liter, bilirubin up to 40 milligrams per deciliter, and triglycerides up to 2,000 milligrams per deciliter. The following drugs that would cause falsely low results for our uric acid determination would be N-acetylcysteine, acetaminophen, metamizole, and acetylparabenzoquinone amine. To sum this up, uric acid is the end product of purine metabolism in humans, playing both beneficial and potentially harmful roles. While it serves as a vital antioxidant that protects the body from oxidative damage, excessive accumulation can still lead to gout and kidney disorders. The balance between uric acid production and excretion is crucial for maintaining health, highlighting its dual importance in both normal physiology and clinical medicine. Once again, thank you so much for listening. I hope you've learned something new from me today. I have placed here, class, the different references that I use, especially for the things that will come out in my examination. So here are not some, but all of my references. Thank you so much again, and God bless us all.